Hi everybody, this is our 16th day of lecture, and we kind of had a crazy week. Last week, I think we got in one day because of the weather, and so that's put us just a little bit behind. I had sent out an email to everyone who had turned in their paper earlier enough that what included homework 2 graded so that you'd have a chance to look over it while we were off, if you wanted to, but you didn't have to. I had postponed via that email message the due date for homework 2 rewrites. So they're due on Wednesday. And if you want to come by and ask me questions, I would really enjoy it if you would, because I'd enjoy it if I could help. So if you are wondering about something, please come by so that I can try to explain it better. Generally, it's easy to understand something one-on-one, and it's easier for me to explain it one-on-one. So I want to emphasize coming by is a good thing. Okay. All right. Also, in that email, I think I had postponed homework 3's due date till Friday. And then I think I made mention of an upcoming test. Is that correct? And so I said that it would be probably on Wednesday. And in the email, I think I included a study guide for that test. I have copies of that study guide, and even if you have it through your email, I'm going to hand you this hard copy. It's back in front. Thank you. Of a study guide for test 1. And this is what I've given pretty much for the last 5 or 6 years as a study guide for this material. Okay, so this is what I've given. And I want to emphasize something for this preparation for this test. I mean, we will be asked to quote facts, quote definitions. And so that's going to be part of what you're asked to do, to state, here's what this completeness property is, possibly. Okay, so you might be asked to state what's the order property on R. That could be something you'd ask to state. Some definitions. Generally, what the test will start off with, problem 1 will be 4 parts to 5 parts, and it'll say, give the definitions of the following terms. Okay? And so I'm looking for you to quote what it means. Mathematicians have spent a lot of time having the definitions of terms be scrutinized and evolve into what they are, so that they describe exactly what they mean to describe. And so they've already come up with the words that best, what they feel, best describes the term, okay, that defines the term. So we're not looking to put them in our own words. We're looking to say, that's what the rate said it was, that's what I'm going to say too. Okay? So I'm looking for you to quote those things. So I would spend a good portion of time, we got a little over a week, of simply memorizing and thinking about what those things mean. So I can quote them, and from the quoting of what they are, think about what they mean. Okay, so that's what we ask. That's the important thing. So if you said, well, what can I do to prepare for this test? I'd know every one of those definitions. I'd be able to state them. Okay, that's what I would do. I know every one of those named facts that I am asking you to be able to state. And a few of them we haven't gotten to yet. For instance, we haven't gotten to, under part 2, the squeeze theorem, but we'll get to it very soon. So that's some information I wanted to give to you about the test. I've given back hard copies of your graded homework 2s, and I want to start today off after saying something about the upcoming test with giving you a chance to ask questions. So if there's something you'd like to ask about, I'm ready to entertain you. Are there any questions? Homework 2 problems, things we've covered in class. Homework 3 problems. Anything you want to ask? Yes, sir.
On the study guide, for part 2, it says be able to state the following named facts. Do you have to be able to prove all of those 2, or just state them?
Just state them. For that part, just state them. Then later, part 3 says, look, I'm going to ask you some of these. Here's what I want you to be able to prove.
Okay.
So I'm narrowing down the material for you, because there's a lot. And I still might ask some things that are off that, but I'd be able to do what I'm asking you. Any other questions or comments? Well, if at some point later on, something hits you to ask about, there's nothing wrong with saying, wait a minute, what about this? Nothing wrong. My job is to answer your questions. Okay? Yes, ma'am?
Sometimes you do things that are more, not out of the book, you do them your own way.
I
You
sure
want
do.
us to know it your way or more like the book?
The answer is, Audra, I want you to be able to prove statements. Or if they're stated in a slightly different way than whichever version you decide to learn, that's okay. What I'm presenting in terms of maybe different proofs, like for instance, I don't think I used the exact same proof about limits being unique for sequences as what's in the book. If you learn the one that's in the book, that proof, and understand that better, wonderful. If you learn the contradiction proof that I proposed to you, wonderful. They're both good proofs. So whatever you choose to do. No, ma'am, I don't have a preference of how somebody does something as long as they do it correctly. That's all. That's a good thing to ask about. And I'm glad you noticed I'm not doing anything exactly like the book. Anybody else with a question or comment? Okay. Well, let's go ahead and get started. You might remember we were in the midst of a proof, and so here, recall, we want to show, so this was step 4 of the theorem, that if the limit as n goes to infinity of x of n equals x, and the limit as n goes to infinity of y of n equals to y, where y sub n is different for 0 for all n known natural numbers, and y itself is different from 0, then the limit as n goes to infinity of x of n over y sub n is equal to x over y. Now, I'm going to write an intermediate step. That's the same thing as the limit as n goes to infinity of x of n over the limit as n goes to infinity of y sub n, which equals to x over y. So this is the intermediate step that I'm adding. We had done some work on that already. I want to go back over that work, and then I want to finish up that proof. So here's the proof. Look on the left. The limit as n goes to infinity of x of n equal to x, and the limit as n goes to infinity of y sub n equals to y, where y is not 0, and for every n element of natural numbers, y sub n is different from 0. That bottom sequence is never 0, and what it converges to is 0. So what we want to do is we want to show that the limit as n goes to infinity of x sub n over y sub n equals to x over y. That's what we want to do. We are trying to show that a sequence converges to x over y. The way that we generally show that a sequence converges has the same kind of standard process. And the first thing we do is we let epsilon be greater than 0 be given. Megan, epsilon being greater than 0 represents the distance. That's what we're thinking. And so we need a k element of natural numbers. That k, John, represents a position in the sequence, such that for all n greater than or equal to k, that means for all positions bigger than k, the terms in that position, so the terms are x sub n over y sub n, minus x over y, what we think it converges to, their distance from each other will be less than epsilon. Less than that positive number's units. Okay, so here, what we do is we know x sub n over y sub n minus x over y. That's the guy we want to be inside absolute values, to be less than epsilon. And since we're subtracting two fractions, we get a common denominator, possibly to try to simplify this. And so here we'll say this is x sub n y minus y sub n x over y sub n. And that's the same thing as that's the value of x sub n, y minus y sub n x over the absolute value of y times y sub n. That's equal. Then I'm going to add and subtract a similar thing from the top and bottom. And so what I'm going to pick is, I guess, x y sub n. Is that what I used before? Megan said yes. It's x times y sub n. Okay. Let's say yes. So we have x sub n y. I'm going to say minus x y sub n plus x y sub n. And then it says minus y sub nx. And then the bottom, in terms of the absolute value of the product, is the same thing as the absolute value of y times the absolute value of y sub n.
I have something different written down. I have before that you subtracted x sub n, y sub n, and added the same thing.
Okay. Then let's do what we had done before. Either way will work. X sub n y.
X sub n, y sub n is what I have.
X sub n, y sub n. Okay.
Yes, sir.
That's fine. There's several ways that we can add different things here, but that's what we've added. Thank you very much, John. Making sure we write down the same things we had. Okay, so this is what we've done before. The top, I can think of these two quantities being subtracted as one number. I can think of these two quantities here that are being subtracted as one number. And so we have a first number plus a second number inside absolute values. And we can apply the triangle inequality to that to say that's less than or equal to the absolute value of the first numbers plus the absolute values of the second numbers. All over the absolute value of y times the absolute value of y sub n. Now what's clear is what can be factored out of the first quantity, that's an x sub n, inside absolute values. Here is a y minus y sub n, and this is over absolute value of y times absolute value of y sub n, and then plus, here what can be factored out is a y sub n, absolute value of that for x sub n minus x, all over the absolute value of y times absolute value of y sub n, which I'll simplify a little further, that this absolute value of x sub n, and I'll rewrite this as y sub n minus y, just to put it in a format that we're kind of standardly used to, over the absolute value of y times the absolute value of y sub n, and then this is plus. Here, the absolute values of y sub n will cancel, and we'll be left with x sub n minus x over the absolute value of y. Now, we're trying to make this quantity be small, the original quantity of the absolute value of x sub n over y sub n minus x over y inside absolute values. We're trying to make it be less than epsilon. And what we have is that original quantity is less than this. So if I can make this be less than epsilon, we will accomplish our goal. That's what I'm thinking. So I want to make, if possible, this quantity here, this addition, will be less than epsilon. What I'm thinking is if I can make, to make this addition be less than epsilon, maybe I can make this first thing in addition be less than epsilon over 2, and the second thing be less than epsilon over 2. And what's promising about this, Adam, is that because y sub n converges to y, I can make this as small as I want. Yes?
Did you pull out a negative? Oh, the absolute value is the same for you.
Right.
I'm sorry.
So, here, and there's nothing to be sorry about. Here's the way I'm going to think of it in a very kind of overview type way. Here, I did pull out a negative, and the absolute value of a negative 1 is just 1, so it doesn't change it. But what this represents, Audra, is the distance that y is from y sub n. But that's going to be the same distance that y sub n is from y. That's the way we can think of it. Okay? We kind of go overview type way. Okay, so look, I can make this be small. I can definitely make this be small. But the problem is that this guy may be getting big, and 1 over y sub n may be getting big. So we can't let those two things happen. Well, first of all, the x sub n's aren't getting that big because we know that they converge. So since the limit as n goes to infinity of x sub n equals that, that is that x sub n is a convergent sequence, then x sub n is a bounded sequence. So what that means by definition, and this is what I want to tell everybody, Adam, when we go and study that from that study guide, the definitions that we got to learn and other information that's listed there, we'll know this definition, okay? And Chuck, it becomes a lot easier. I'm going to tell you, when I took this class, I didn't do too much preparation until a little while before the test, and then all of a sudden I started learning these definitions. I was like, oh my God, I understand why they're doing this. But without these definitions, it didn't make sense to me. Without these facts, I didn't know. So I hadn't studied very much. But after the time I started studying, I said, oh, I see what they're doing. So please start learning these definitions if you haven't already. There exists an m that's greater than 0, such that the absolute value of x sub n will be less than or equal to m. And that's true for all n element natural numbers. So for all terms of the sequence x sub n, inside absolute values, they're going to be less than this m. Okay, so this thing that we want to make small, x sub n over y sub n minus x over y, that's going to be less than or equal to replacing the absolute value of x sub n by m. It's m times the absolute value of y sub n minus y over the absolute value of y sub n, and here plus the absolute value of x sub n minus x over the absolute value of y. Okay, now, again, I've handled one of the problem spots that we had, and this was already done. And that was, I replaced the absolute value of x sub n by something that was bigger than n, that's fixed, that doesn't change based on n. But I still got something in here that might get really big, 1 over y sub n, that could cause this part not to be less than epsilon over 2. Okay? So I need to handle it. So the next thing that I want to consider is, we will consider the absolute, 1 over the absolute value of y sub n. And show that that 1 over the absolute value of y sub n is less than sum t. So I'm going to put a bound on this thing. Somehow I'm going to say it's got to be less than or equal to this number. So that I will be able to replace 1 over the absolute value of y sub n by a t, and then get everything that I want in terms of just y sub n minus y and x sub n minus x, which I can make as small as I want, like I want far enough along sequences. So how come this will happen? Okay, first of all, note y, what it converges to, this is the sequence of y sub n, y is different than 0. I know that. I don't know if it's positive or not, but it's different than 0. And so then, the absolute value of y over 2 is going to be bigger than 0. Okay? So y is different than 0. Take the absolute value of it, that's going to be bigger than 0. So the absolute value of y over 2 is bigger than 0. The only way the absolute value of y over 2 is equal to 0 is if the absolute value of y is
0. But that can't happen because y is 0. So, since the limit as n goes to infinity of y sub n equals to y, by definition, so again, once we start having these definitions memorized, there exists a k, element of the natural, I'll call it k sub 1, element of natural numbers, such that for all n bigger than or equal to k sub 1, the absolute value of y sub n minus y will be less than, well, any epsilon that I had picked, okay, in the case of 1 would depend on the epsilon picked, the epsilon I picked is the absolute value of y over 2 because it's positive. Now I'm going to have a series of statements that have to do with all n bigger than or equal to this case of 1. So for all n bigger than or equal to this case of 1, I can rewrite this as a statement that doesn't involve absolute values. That is that we have minus absolute value of y over 2 is less than y sub n minus y, which is less than the absolute value of y over 2. That's from the famous statement that we've had dealing with inequalities involving absolute values. This is a compound inequality. We'll go right from that type of statement. Okay. So if I solve for y sub n, I would add y to both sides. So for all n bigger than or equal to k sub 1, we have, so if I add y to both sides, I get minus the absolute value of y over 2, I'll write it this way, plus y is less than y sub n, which is less than the absolute value of y over 2 plus y. I kind of like to get a bound on the absolute value of y sub n's in some sense, or 1 over the absolute values of y sub n, that's what I'm looking to do. But one thing in terms of getting the absolute value, I don't even know whether this quantity right here, I don't even know whether that's positive or negative. I don't. Because if y was minus, let's say y was minus 4, the absolute value of minus 4 would be 4. 4 divided by 2 is 2. 2 plus minus 4 is a negative number. It's minus 2. I don't even have that this is positive. Is that okay with everybody? I don't know. I don't know what to do. So here, I would like to break this down into cases maybe about y itself. So let's say have case 1. Let's suppose, let's say y is greater than 0. What if it's positive? Okay. Then, this would say minus y over 2, that's what that guy would be, plus y is less than y sub n, which is less than y over 2 plus y. And that's true for all n greater than or equal to k sub 1. So, for all n greater than or equal to k sub 1, here, this is the same thing as y over 2 is less than y sub n, which is less than 3y over 2. And that gives me two statements. So, for all n greater than or equal to k sub 1, and that's the setting for which everything I'm writing pertains to, so I'm not going to write it anymore. That's what it's doing. I'm just going to have a bunch of implies here. What we have is, we have y over 2. Well, first of all, let me write this one thing down that should be noted. At this point, look at y over 2. We're assuming in this case that y is what kind of number? Positive. So y over 2 is what kind of number? Positive. So for all n bigger than or equal to k sub 1, y sub n is bigger than this positive number. That makes y sub n itself be positive. That's what I'll say. So let's just make sure that we know that's greater than 0. Okay. So here, so for all n greater than are equal to k sub 1. Okay, we have it. What do we have? All right, well here, if I multiply everything by 2, we have y is less than 2y sub n, which is less than 3y. I'm going to divide everything by y, which implying, if I divide everything by y, I have 1 is less than 2y sub n over y, which is less than 3. And then, which implies, okay, now I'm going to divide everything by y sub n. So 1 over y sub n will be less than 2 over y, which is going to be less than 3 over y sub n. So in particular, what I'm going to pick out of this inequality, this compound inequality, is the first part that's listed there.
So we don't really care about the 3 over y. That's not useful.
That's not going to be useful for us in this particular thing. Remember, my goal here is I'm erasing it on this side, but I'm supposed to come up with some positive number that's bigger than or equal to 1 over the absolute value of y sub n. Okay, that's what I'm trying to do. And I want to do that for all n, for every term in the sequence. I can do it for every term in the sequence. Okay, thus, for all n bigger than or equal to k sub 1, so as long as you're further than that spot in the sequence, we have 1 over y sub n is less than 2 over y. But here's what I want you to notice. Y sub n, for all n bigger than or k sub 1, bigger than or equal to k sub 1, were positive numbers. So y sub n is the same thing as the absolute value of y sub n. Is that okay? So this says that 1 over absolute value of y sub n is less than, and y in this case was what kind of number in this case? Positive. So this is 2 over the absolute value of y. Because the absolute value of y is y. Is that okay? That isn't my T maybe, but that's what I got for right now. Okay. Case 2. So here, I'm going to circle this one. That's my circle. Case 2. Case 2 is suppose y is less than 0. Okay. If that's the case, then looking back where we were, then for all n bigger than or equal to k sub 1. Okay? So, for those of you in the classroom, I'm looking here. This is where I'm looking, and I'm working under the condition that y is a negative number. Okay? So here, what is the absolute value of y? It's not y anymore. It is minus y. So the absolute value of something is either itself or minus itself. It's itself if itself was positive. It's minus itself if itself was negative. So here, rewriting this, I have minus a minus y over 2 plus y less than y sub n is less than minus y over 2 plus y. So for all n bigger than or equal to k sub 1, here, let's see, this is going to be 3y over 2 is less than y sub n is less than, this is just going to be y over 2. So for all n bigger than or equal to k sub 1, if I multiply everything by 2, I get 3y is less than 2 times y sub n, which is less than y. Now I'm going to divide everything by y. But wait a minute. Y is what kind of number? Negative. That's right, negative. So I got to flip the inequality. Okay? Beforehand, y was positive, so I didn't have to worry about flipping the inequality. So for all n bigger than or equal to k, so 1, what we have here, I'm dividing by y, so this would say 3 is bigger than 2y sub n over y, which is going to be bigger than 1. Now I'm going to divide everything by y sub n. And I really omitted something, so I'm going to come back to this. So I'm going to come back here. Okay. Note, for all n bigger than or equal to case of 1, y sub n is less than 0. Okay, I've written it down. Let me get out of the way. What? Where did he come up with that? Here's where I came up with it. Here's the statement for all n bigger than or equal to case of 1. 3 times y divided by 2 is less than y sub n is less than y over 2. What kind of number is y over 2 in this case? It's negative. And y over n is less than this particular negative number, so that means it must be negative. Is that okay? Okay, so that's what I've got. So now I'm going to divide everything by y sub n from the last inequality, what I've written here. Okay? And so I'm going to have to switch the signs again. Thus, for all n greater than or equal to case of 1, here when I divide by y sub n, I'm going to have 3 divided by y sub n is less than, here it's going to be 2 over y, which is going to be less than 1 over y sub n. Okay, I'm going to look at this second part again, this part this time, to the right, but it involves y sub n. And so, thus, for all n bigger than or equal to case of 1, what we have is 2 over y is less than 1 over y sub n. So, for all n bigger than or equal to case of 1, so what I want to do is involve the absolute value of y, or an absolute value of y sub n. Okay? But y and y sub n in this case are both, for n is bigger than or equal to case of 1, are both what kind of numbers, Chuck? Negative. Negative. And so if you want the absolute value of these quantities, they're not themselves, they are minus themselves. And so I need a minus involved. So I'm going to multiply both sides by minus 1. What I'm going to get is, if you will, I'm going to get 1 over minus y sub n is going to be less than 2 over minus y. That's what we're going to get. So, for all n bigger than or equal to case of 1, we have 1 over the absolute value of y sub n, because the absolute value of y sub n in this case is minus y sub n, is going to be less than 2 over the absolute value of y. I'm going to circle this. That's my circle. If you compare the two circles, you see that they are the, say it again, John.
The same.
They're the same. So in all cases, I have this inequality. All cases, for all n bigger than or equal to case of 1. So you've got to go to some spot in the sequence. But after that spot, 1 over the absolute value of y sub n is going to be less than 2 over the absolute value of y. Okay, so now what I'm going to let t be, we're going to let t be equal to the maximum of 1 over the absolute value of y sub 1, comma, 1 over the absolute value of y sub 2, comma, all the way up to 1 over the absolute value of y sub case of 1 minus 1. And then, after that, we're going to have 2 over the absolute value of y. Thus, for all n bigger than or equal to case of 1. Okay? No, I'm sorry. Thus for all n element natural numbers. Sorry. 1 over the absolute value of y sub n will be less than or equal to 2. So, we have the absolute value of x sub n over y sub n minus x over y is going to be less than or equal to. I think we had an m. I think I had x's here. I might need some help. X sub n minus x, I think. I think I had absolute value of y. I think I had the absolute value of y sub n here.
I think
But-
it was with absolute value of y
Y sub n minus y.
This was y sub n minus y. Thank you very much.
And then the bottom was that times absolute value of y sub n.
Okay, so really, the absolute value of y sub n that we had, let's just put it there. Let's put it this way. Let's put it as 1 over the absolute value of y sub n, like that. Here's the absolute value of y. Plus, this must have been the absolute value of x sub n minus x, is that right? Over the absolute value of y, is that what we have?
Yes.
Must have been what we have.
Yes.
And so, look, this part right here, 1 over the absolute value of y sub n. 1 over the absolute value of y sub n. What can I replace it with that makes it bigger?
T.
T. So this will be less than or equal to t times m times the absolute value of y sub n minus y. And let's put over the t times m, the absolute value of m, plus x sub n minus x over the absolute value of y. Now here's what I'm thinking. This guy right here is nothing more than a, yeah, it's a constant. This y, absolute value of y, is a fixed number. So these are all fixed.
So we're in good shape.
Yes, that's right. I can make this be small as I want. I can make this be small as I want by going far enough along in each sequence. And so here's what I'll say. I want this whole thing to be less than epsilon over 2. So there exists a case of 2 element natural numbers such that for all n bigger than or equal to case of 2, the absolute value of y sub n minus y, what do I want it to be less than? I want it to be less than epsilon over 2. But I want, not only that, I want to involve these quantities here so that they'll cancel out when I make this replacement by something bigger. So I think I want a t, I want an m, what else do I want?
Absolute value of y.
In the top, okay? That's true since, why is that true? Why can I find that case of 2? Since, why is that true? Why can I find that case of 2?
Since y sub n converges to y.
That's right, John. Since the limit is n goes to infinity, y sub n equals to y. Similarly, just in case you're wondering, there's no way I'm going to ask you this problem on the test. I'm not. Since the limit as n goes to infinity of x sub n equals x, there exists a case of 3 element natural numbers such that for all n bigger than or equal to case of 3, I'm looking back over here, I can get that the absolute value of x sub n minus x, I need it to be less than, I think, epsilon times absolute value of y over 2. So that when I make that replacement, we're good. Look, the two things that I want to make happen, which I can make happen at different spots. So to make them happen at the same spot, what do I let k be? We've done this now, this will be the third time. Let k be equal to the maximum.
All the numbers we talked about.
Yes, but I'm just going to worry about K1 and K2 because the other one, K2 and K3, because K1, we just got one t that worked. So let K equal to the max of K1, K2 and K3. I mean, if you you work some problem that's so long, you might get K sub 9, you might get K9 up there, and you think, dog. That was really bad.
Did you use that one in other classes?
I don't know. The ones that I've used in other classes, Adam, that I know I've used, I don't think I've ever used that. The one I've used in other classes is that sometimes we'll do a problem, and it have multiple parts. And like, if you have problem 3, it's got 3A, 3B, 3C, 3D. I said, well, let's do 3D. You gotta be careful, this problem comes right at you. 3D.
Do they get it?
They get it, but they just groan. I mean, it's not funny. I mean, when people are nice to me,
It's subtle enough that it's good.
I don't know. I think it's terrible. But that's my sense of humor. It's things like that. I do think it's funny. But, you know, it's not. I mean, everybody knows it's not. I just drive my friends bonkers with these types of things. I like it. For all n greater than k, x sub n over y sub n minus x over y, which is less than or equal to what I had written over here, t times m, which we'd already found, absolute value of y sub n minus y over the absolute value of y, plus the absolute value of x sub n minus x over the absolute value of y is going to be less than, let's see, I've got t m less than, it's going to be strictly less than, okay, t m over the absolute value of y, and I'm going to replace y sub n minus y by what is bigger than it, which was epsilon times absolute value of y over t m times, one more thing down here. 2. That's right. Plus, this guy right here is going to be less than, well, it's 1 over the absolute value of y. That's this part right here. 1 over the absolute value of y. The absolute value of x sub n minus x I'm going to replace with something bigger, which was epsilon times the absolute value of y over 2, which equals to epsilon over 2 plus epsilon over 2, which equals to epsilon. So, what happened here was, I wanted to show that x sub n over y sub n minus x over y inside absolute value was less than epsilon for all n's bigger than some spot. I did. So that means the limit as n goes to infinity of x sub n over y sub n equals to x over y. And that's the proof. Okay, it took us a day and a half to do it, but there it is with all of its details. Okay, in homework 3, I'm asking you to do a certain problem, and it has to do with showing that a limit of the sequence converges. And I want to do something similar to it to end this class period with, to kind of help, okay? Give you something to manipulate. So here, as an example, I want us to show the limit as n goes to infinity of 5n plus 7 over 8n minus 3 equals to 5/8. So I'm going to prove that. And that's to help us with a homework problem for homework number 3. That's right. I hadn't done one like this, I'm going to do. Okay, this is the way I'm going to do it. So proof. I'm going to, well, I know what I'm going to do because it's always having kind of standard format for doing this. What's the first one? That's exactly right. And listen, I want to tell everybody, it may sound silly, but that's part of the training, to say, I know what we're going to have to do with the segregates. So we're learning something. What do we need? That's right, we need a case. It's a natural number such that for all n bigger than or equal to k, that's the value of 5n plus 7 over 8n minus 3 minus 5 over 8 is less than epsilon. That's what I want. Let me give everybody a second to catch up. And then I'm going to work with that quantity of trying to make it smaller than epsilon. Okay, so note, 5n plus 7 over 8n minus 3 minus 5/8 is the same thing. What I would think here is that I'd like to get was natural. Not everything that we do that's natural is beneficial, okay? But in this case, it is. When we're trying to subtract two fractions, we need a common denominator. So yeah, I'm going to do that. 8 times 8n minus 3 is going to be the common denominator. So it's 8 times 8n minus 3. And what I'd have to multiply this by 8. So I'd have 8 times 5n plus 7. And then it would be minus 5 times the quantity 8n minus 3. That's what that is. So that's the same thing as, let's see, this is 40n plus 56 minus 40n, then it's plus 15 over this, let's make this 64n minus 24. Golly, terrible. Sorry. Okay, and so that's equal to, so I need to look, it's the absolute value of, let's see, 40n minus 40n, that's going to kill each other. We got 56 plus 15, I think. Isn't that 71? Over 8 times 64n, no, it's not 8 times, it's just 64n minus, okay. Now, what kind of numbers are in? Yeah, they're positive. They're natural numbers. That's the better story. They're natural numbers. So think about every natural number you could stick in. You multiply by 64 and you take 27 from it. What kind of number is that? It's positive. And if I divide that into 71, it's positive. So the reason I'm trying to notice that is because really, I don't want to work with absolute values. I want something that doesn't have absolute values. And it turns out what we're taking the absolute value of is a positive number for all natural numbers. And so that means that it's the same thing as 71 over 64 n minus 24. So we want 71 over 64 n minus 24 to be less than, what do we want?
Epsilon.
Epsilon. So we want, I don't have this, I'm trying to get it. We want 71 to be less than epsilon times 64n minus 24. That says we want, I'm going to solve for n. We want, here this would be 71 over epsilon to be less than 64n minus 24. I'm going to add 24 to both sides. So we want 71 over epsilon. Now, if epsilon is really, really small, 71 over epsilon is huge. Plus 24, that's even huger, to be less than 64 over n, or 64 times n. So we want, I'm almost done. So we want, I divide by 64, we want 71 over epsilon plus 24 divided by 64 to be less than n. How do I know that I get any natural number, that I get a particular natural number? How do I know that there's a natural number that satisfies this inequality?
Archimedes property.
That's right, the Archimedes property, which says the natural numbers aren't bounded above. There exists a k on natural numbers such that 71 over epsilon plus 24 all over 64 is less than k. So for all k, so for all n bigger than or equal to k, we have, and this is what I wanted, 71 over epsilon plus 24 over 64 will be less than even. That's what I wanted, that's good enough for me, and so that's why I'm going to prove, okay? If you wanted to work backwards, you could, but I'm good with that. Ladies and gentlemen, that's what I have for you today. Thank you very much for your time and patience.